Maybe it's an unpopular opinion, but I think that one of the lesser tragedies of the pandemic, and I said lesser, but I think it's still a tragedy, is that Greek letters have slowly been turning sinister. If you're in a technical field, you're going to learn some Greek eventually, and I like Greek letters. And it's been sort of sad to see over the past couple of years that now there are some Greek letters that I have to be careful about using. So first we lost delta. And I like delta. And now if I say delta in polite company, people get sort of terrified because they think I'm talking about COVID. But at the time I was like, okay, so they've decided to call it delta, whatever, fair enough. And then we lost Omicron. And I like Omicron. There's something sublime about the simplicity of Omicron. I like it. And I can't talk about that in polite company now either. And it's worse because there's a lecture video out there from last summer where in the middle of like an hour-and-a-half long lecture, I have this tangent where I talk about my favorite Greek letters. And obviously that hasn't aged well. And fortunately, nobody watches those videos, so it really doesn't make any difference. So I don't know. And the pandemic's been hard on all of us, even Greek. And so all I can hope for, really at the end of the day, all I can hope for is that when you watch this video, whenever that is, I mean, I guess I could hope that you watch this video, but that might be hoping for too much. So hoping that when you watch this video, whenever that might be, that lambda, the Greek letter lambda, hasn't turned sinister yet. Or that if it has, if one day, and they will, one day they name some kind of variant of something after lambda, that's one of the ones that nobody remembers afterwards. There were all sorts of variants between Delta and Omicron, and to be clear, they were bad. But it didn't enter our consciousness the same way that the letters Delta and Omicron did. And now we've got to be very careful about using those letters. I think Lambda is a really cool letter. I think there's something about it that's so mysterious that really makes it fit well with our next topic, which is something called a Lambda Expression. And it used to be when you start talking about lambda expressions in C++, everybody perks up because that sounds mysterious and exciting. And now they hear Greek letters and everybody thinks the worst. Let's just hope it's no worse than it is now when you finally watch this. So, what I have on the screen right now is a sort of excerpt of an earlier example. You might recall the is-even function from our earlier adventure with decoupling that all and any function from before. And in fact, the all-of function, the end result of that exercise, actually is a guest star in this. We're just going to scroll down and it's never going to appear again. And so the task seems deceptively simple, and it's one of the usual sort of contrived tasks we use to introduce notation. And the task is remove this function definition. And I'm always happy to comply. We'll just go ahead and do that, and we will hit compile. And of course it complains. It says, I'm sorry, what is even? You deleted it. Well, it's fair enough. So it's not just to remove the function definition, and really, I mean, you look at that and you would say, why ever would I want to remove this function? It's 3 lines, it's already written, the code works, what's the point? Fair enough. I want to introduce some notation. You got to do that somehow. I want to remove the function because I want to make the point that maybe all of is useful everywhere in my program. There are lots of times I want to ask if every element of a vector has a property. But maybe the properties I'm asking about are specific. I suppose whether or not a number is even isn't too specific a thing. But if I have a huge program that uses the all of function in lots of places, maybe the conditions that it's testing are very specific, and they're dependent on the types of the vector, they're dependent on the context. Maybe I don't want to pollute my global namespace with tons and tons of these tiny little functions to test conditions. And also, if the main function's really long, maybe I don't want to have to scroll all the way up to write my condition functions. Wouldn't it be great if I could make an even lighter weight function? I could make a function wherever I need it, and the function only exists for as long as I need it, just like variables. So in main, I've got these vectors v0 through v3. v0 through v3 exist during the scope of main. That's how variables work. Scoped allocation. They come into existence when I create them. They cease to exist at the end of the scope. I don't have to worry about the rest of my program getting confused about there being some global variable called v2. If I'm beginning to treat functions as data, I need to make sure I do that uniformly. Functions have to be on equal terms with other data, which means if I think it's bad to have a global variable that's a vector, I should also think it's bad to have a global variable that's a function. If I only need the function in one place, maybe I just want to create the function in that place and have it live as long as wherever the code it's being used lives. And it turns out I can do that. In C++, I'm allowed to create functions wherever I want, using something called a lambda expression. Now, we don't actually have to write the Greek letter lambda. We just say lambda. It turns out we never even have to write the English word lambda to write a lambda expression. And so we'll start in this initial example writing a very simple lambda expression. I'm going to call the function isEven. I'm going to use a C-style assignment here. And I think this is a case where it's justified. It's because I'm going to need curly brackets in a minute, and it's going to look really weird if I don't use a C-style assignment. And because I also want to make it very clear that I'm assigning the function I'm about to create to the variable called isEven. So I write this. I want to ask if an integer value x is even. And so I write what looks sort of like a function signature. Almost, although I don't see a return value. And we'll see in a minute we don't need to provide a return value. Before I write the list of parameters, I put these two square brackets. Now, I will actually put something inside the square brackets shortly. But for now, when you see an opening square bracket with nothing before it, what you're really seeing is the beginning of a lambda expression. And the lambda expression lasts from the beginning of that opening square bracket to the end of this closing curly bracket, which will contain the function body. And so I'm just going to write the body of the isEven function. And there it is. And to be clear, this is the lambda expression, everything between the square bracket and the curly bracket. The semicolon is because I'm actually at the end of an assignment statement. This whole thing is actually just the assignment statement on line 28, the C-style initialization that I'm writing as an assignment. And so, of course, like any assignment statement, there needs to be a semicolon at the end. But the lambda expression is this. This is defining a function that is being created for me on line 28. The function does not exist until I reach line 28. And the reason that that's so powerful is it means that how the function comes into being can be influenced by what's already happened in my code. And we'll see that in the next few examples. So here I create a new function called isEven that takes an int and returns oh wait, we never got around to that. What does this return? Well, here I have not specified a return type. And maybe I'll let the compiler sort of show us that I don't need to. And the code compiles, and I run it, and it prints out, okay, is v2, I guess I should say, it says isEven, but it's asking, is every element even? Every element of v0 is even, every element of v1 is even, every element of v2 is even, but it's not true that every element of v3 is even. And so I think the code is working correctly. I have synthesized my own function object during the execution of my code in main. And we'll see later, I'm even allowed to have this lambda expression be influenced by stuff that's already happened in main or variables that already exist in main. I'm allowed to bring them into my lambda function. That brings us to the return type. So what is the return type of the lambda function? Well, in this case, the all-of function expects a function that takes an int and returns bool. And if I look at this, even if I don't specify a return type, what I'm returning is the result of this expression, which we know in C++, relational operators like the equals equals operator return bool. And so the return type of the function appears to be bool. By human inspection, we think this function is trying to return a bool. And the compiler agrees. One other great thing about lambda expressions is the compiler can deduce their return types. Now, you are allowed to use your own return type if you insist. If I say, I want it to be absolutely clear, I don't want the compiler to get confused, this returns bool. You use this odd arrow notation for that, but you are allowed to do that, and we'll just show that off. All right, and so that works. However, when at all possible, you should write your lambda expression to have no explicit return type. Let the compiler deduce it. We've already learned the compiler is very good at type deduction. The only time you really need one of those things, one of those explicit return types, is when the compiler somehow gets confused. For simple lambda expressions like the ones we're going to write in this course, that pretty much never happens. All right, so what I've shown in this first example is that I can create functions on the fly. I can create a lambda function whenever I want. With this lambda expression notation, I can then assign it to a variable. We already know that functions can be assigned to variables. I can now create functions on the fly. Now, it remains to be seen what exactly those square brackets are for. If you want to know what the word lambda is supposed to mean in all of this, it turns out that's actually not a C++ term. That goes back to something called the lambda calculus, which is a very big deal in theoretical computer science and in other programming languages because they've implemented the lambda calculus. It turns out, though, it's not really a C++ thing. The term is used because it comes out of the history of computer science. It's a term that was already used in computer science before C++ existed, or indeed before modern computers existed. What else can I do with lambda expressions? Okay, how about this exercise? And we're going to see here this function, this sort of meaningless function called for each. This is actually sort of a play on a standard library function called for each that is equally sort of trivial. You'll see functions like this a lot in the next few videos because a common style of exam question in this course about functional programming and lambda expressions is to give you a function like this and then expect you to complete an exercise without writing any loops of your own. In other words, to call this function every time you want a loop. It's contrived, but we have to test these concepts somehow. Okay, so the next task is create a lambda function called printInt, which takes a single integer value and prints it out. I will then pass that function, which apparently, given that I'm using it with for each, I'm going to pass the function into the for each function, and the function is supposed to take an int, one element of my vector, and return void. Okay, so I'm going to make a lambda expression called printInt. I'm going to get around the weird indentation there. And it's going to be a lambda expression. It's going to take one int as its argument, and it's going to print it out. And this is just to prove that I can write lambda expressions that have a return type of void. So I print out x, and I print a space. So obviously, if I stare at this, there's no return statement, and that implies to me the function doesn't intend to return anything. And so it's logical the compiler will deduce this is a lambda expression that returns void. And therefore, it meets the criteria required by the argument to for each of being a std function object that takes an int and returns void. Okay, so I'll try running that. That's lambda 2. There it is, and it prints 6, 10, 17. Now, obviously, there's a missing new line there. Maybe we'll just put that at the end, so we'll just add that in ourselves. The printInt function just prints an int, so I suppose we shouldn't reasonably expect that it should print a new line. But for the sake of the output looking clean for the video, yeah, there it is. So I'm able to print out every element of my vector. I have this function I've written called for each that takes a vector and a function to call on each element, and then it just calls the function on each element, which seems a little bit unnecessary, but it is a valid use of functional programming techniques. I then write my own lambda expression called printInt, and all it does is take an int and print it out using cout, and then I use for each to actually iterate over the vector and do that. So here, inside of main, I don't use any loops, but I'm able to iterate over the vector with the help of this helper function called for each. So I just wrote two different, very simple lambda expressions. And one of the benefits of a lambda expression is it's an anonymous function. It has no name of its own. It only exists for as long as the scope that contains it. So I define it in main, and it will exist for the remainder of main, the lifespan of the variable I assign it to, and that's it, which is helpful because if I make lots of tiny functions, as I will do when I'm throwing functions around my program like data, I don't want to have to make a global name for all of them because that's going to make a mess. Okay, what else can I do with lambda expressions? Well, here I have this basic piece of code. So I have a vector of 6, 10, and 17, just like before. I've got a variable called the sum, and I've got my for each function. So the for each function takes a vector, it takes a function to call, and then it calls that function on every element of the vector. A bit contrived, but something that's in the standard library, so I guess it's a reasonable thing to have here. What I would like to do now is write a lambda expression and assign it to a variable called sumItems. Okay, and I want it to do the following. It takes a single integer value, so an element of the vector, and then it adds it in to my variable the sum. So my goal is, once my for each function is done executing, this variable the sum contains the sum of all the elements that were iterated over. So everything on which I called my lambda function. So I just take a shot in the dark here. I try this. I say, well, okay, here's my lambda expression. I'm writing the lambda expression in the scope of main. If it works just like any other nested scope, that means that if I try and use the name the sum inside of my lambda expression, it will resolve to this variable out here, which is sort of amazing. I can't do this with functions I define outside of main. Am I actually allowed to borrow things from the scope of main? And the answer is yes, but we're not quite there yet. Let's try compiling this. So it's natural that we should think that I should be allowed to borrow things from the outside scope because the lambda expression is inside of main. I should be allowed to use anything in the scope of main. And I sort of am, but not just yet. So on line 25, I get this error. The sum is not captured. Is not captured. So this isn't saying the variable's undefined. We know what happens if I'll make a new variable called the other sum equals 6. Okay, so let's just look at the error that the compiler gives us when it can't find a variable. It says, yeah, the other sum wasn't declared in this scope. That's the warning or error we're used to getting when we use a variable name that does not exist. But here I compile this. It doesn't say the sum doesn't exist. It says it's not captured. And of course, we should look at that as curious scientific people and say it's not captured. So I suppose now there's something called capturing, huh? I want to find out what that is. What does it mean for the sum to be captured? And what I want to do is have my lambda function borrow some things from the scope in which it was created, to capture them. And I'm allowed to do that. So the idea behind this lambda function is I have this function for each. And for each knows nothing about main. What I want to do is package up some lambda function and hand it over to for each. And then for each just calls it. For each has no idea what the lambda function does. When I package it up, though, it has to be packaged up for transit. When I finally pass it into the for each function, it has to be ready to be passed outside of main, to leave the scope of main for a minute to be used elsewhere. That does require a little bit of advanced preparation. When I create the lambda function, it's being created in the scope of main. But when the lambda function gets called, it may no longer be in main. The lambda function gets called from some distant locale. It gets called from the for each function. So I am allowed to borrow things from the scope of main. But if I do that, I have to explicitly indicate that I want to do so. We call this capturing them. If I want to use something in the outside scope, I have to capture it into my lambda expression. And I can do that in two ways. The first way is to capture a copy, to capture by value. If I put the sum in square brackets, what I'm telling the compiler is when I use the name the sum inside of my function, what I'm really doing is I'd like you to make a copy of this variable at the moment the lambda expression is created so I can use it inside. Because it doesn't make sense to make a copy and then modify it, the compiler sort of thinks you're weird if you try and modify your copy. And here it says, yeah, by default, when I try and capture a variable called the sum from main, by value, capturing a copy of it, it is captured as a constant copy. And the compiler gives the same warning or error it always gives when you try and modify a constant variable. It says, wait a minute, you want to make your own copy of this variable and then modify it? What's the point? Your copy gets destroyed when your function ends. So the alternative is, if I would like to borrow something from the outside scope and modify it, I obviously want to modify the original. So I want to capture it by reference. And so you write this. And in this context, that is what I want to achieve. I would like to modify the original variable called the sum by reference. So whenever you call sum items, I want to modify something that actually originated in the scope of main. So to package up a lambda expression that allows it to modify things that live inside of main, I must capture them into the lambda expression, package them up for transit. And I want to capture them by reference because I want the modification on line 25 to apply to the original variable called the sum. When you capture something by value, you are making a copy and the copy is read-only. So if I want to modify it, pretty much I have to capture it by reference. And so I'll try that out. We can see it works. And when I call the function, we notice the sum is 33. This is amazing. Even if you didn't believe my long videos about decoupling stuff, even if you didn't think that that was a good application, this is something you were never able to do before. Deep inside of this other function for each, or maybe across layers and layers of function calls, I am able to package up a piece of actual code and send it across layers of other function calls. When this function, this lambda expression eventually gets called, I am allowed to borrow something from the scope of main. The for each function knows nothing about main whatsoever. The for each function has no idea that main contains other variables. And yet, deep inside of the for each function, it calls this lambda expression that can come back around and modify things from main. That is amazing. We have not yet seen anything close to that level of flexibility. The closest thing we've seen is the ability to package references into objects of a class type. So if you go back and look at the video where I wrote an iterator, I did something similar. But to do that, I needed a lot of machinery. Here, I am doing it in 3 relatively simple lines. I'm also going to bring up something else. So I'm defining on line 24 a function. The function takes a parameter x. Whenever the function is called, at the moment the function is called, the value of x is determined. That is determined at the time the function is called. We know how function calls work. I mentioned last week that You can also provide arguments to a function with angle brackets, the templates. And of course, templates are resolved when the function is compiled. And now we've got square brackets. And notice that I'm, in a sense, providing an argument to the function in these square brackets. I'm saying to the function, you get to use my variable, the sum, by reference. And so I'm going to claim, as part of my grand unified theory of function arguments, that angle brackets, square brackets, and round brackets are really all on an equal footing. They're all different ways of passing arguments to functions. The arguments you pass in angle brackets get resolved at compile time, when the function is compiled. The arguments you pass in square brackets get resolved when the function is created, which may not happen at compile time. And finally, the arguments you pass in round brackets get resolved when the function is finally executed, when it's called. A function is only compiled once and only created once. Those may not happen at the same time. It might be called thousands of times with different arguments. And now I've got ways of passing in parameters at compile time, at creation time, and when the function is finally called. They're really all just special cases of the same concept of parameter passing. But we're not quite done. What about this example? Okay, so again, the for each function. Now I've got a function called search. And my goal here is, oh, there's some icky sort of tabs left in from when I converted this exercise. I will shamelessly admit this is an exercise I have used in the past, long before I was a convert from tabs to spaces. I'm admitting that so late in the course that nobody who cares is even watching by this point. I have this vector v. It contains the elements 6, 10, and 17. And all I want to write is a Boolean function called search. It takes the vector, it takes an element, and it answers the question, yes or no, does this vector contain this element? And instead of printing out the Boolean value as an int, 1 or 0, I actually use if statements to say yes or no. Does it contain 6? The answer should be yes. Does it contain 10? The answer should be yes. Does it contain 187? The answer should be no. So all I have left to do is to write this function search. Now, this is a contrived task, and you can see, write the function without using loops. Obviously, programmers are allowed to do whatever they want. If the language allows it, you can do it. There are reasons why one feature might be better than another. So we saw last week, there are reasons why you might want to use recursion instead of loops, but you can do whatever you want. You can mix and match loops and recursion. You can mix and match functional constructs and loops and recursion in whatever order you choose. For the sake of a course like this, I have to ask you exam questions that force you to use functional features, because otherwise I don't know that you can use them. And it's the usual problem with exams, which is that all exams are artificial. Obviously, you might write code on paper if the exam is in person. Who knows what's going to happen at this point? You might write code in some web form somewhere because it's an online exam, but ultimately, exams do not reflect programming practice. A programmer in practice has the ability to Google things, to ask their colleagues how to do things, to meditate on their solution overnight, to sleep on it, and to evaluate things, to post their code on the internet and ask for help. None of those things are allowed during exams, and that's one of the reasons why exams are artificial. They are a necessary evil. That is the case in pretty much all fields, though. I don't think there's any other field you could go into where, reasonably speaking, you get a career in that field and your job consists of answering Scantron exams, or where your job consists of writing essays in 90 minutes. Give me a break. That's just the way education has to work. There are some things that are contrived, and I'm evidently willing to admit that in the course of, what, a 2-minute tirade, as I've now done. So unfortunately, there are going to be some contrived questions. I take a certain amount of pride in the fact that up until a point like this, so for all of 111 and the majority of 116, I have generally given exam questions that amount to just make this work. Write any code that answers this question. And if I want you to use a specific technique, I will try and design a problem that requires it. But if you try some other way and it works, you get the marks. Unfortunately, finally, I have to impose arbitrary restrictions. So a common exam question you might get in this point in a course like this is, perform this task. Write this function, but don't use any loops. You can use the for each function, so you can use functional stuff, or you can use recursion, but you cannot use while or for. In a question like this, you are allowed to call the for each function. That doesn't count as using a loop. The for each function contains a loop, but you are not writing a loop by calling it. So I'm going to use functional semantics to implement this. So how do I search a vector? Well, if I used a loop to search the vector, what I would do is iterate over each element and ask the question, is the element I'm looking at the element you are looking for? And if so, then I guess I'm going to return true. The element was found. If not, I keep going. If at the end I still haven't found the element, then the answer is no. The answer is no on all counts. The element is not in the vector. So I'm going to try and use the for each function to search my vector. I want to iterate over each element, and for each element, I want to ask the question, does it equal the thing you gave me? Actually, for clarity, I'm going to call this search element. So I can use a Lambda expression for that. I want to pass into the for each function. I'm going to call this search function. Okay, so I'm going to just sort of mock this up. I take one element of my vector called x, and now I'm going to ask the question, is x equal to my search element? And if the answer is yes, then I do something. Do I return? No, I don't think I can do that. A return statement on line 24 would return from the lambda function. What I want to do is return a value from my original search function. Okay, so I'm not going to try playing with return statements here. Instead, I'm going to try this. I'll say, how about I'm going to return a bool eventually. So I'll say bool, did I find, no, that's stupid. Okay, bool found equals false. We'll use uniform initialization. Okay, so I make a variable called found, which is set to false. And I'm going to return that at the end. Okay, so my goal basically is my search function has a variable called found, and I'm going to iterate over the vector. If ever I see the element I'm looking for, I will set found to equal true. So I want something like this, basically, in my lambda expression. I look at each element x, and I check, does this equal the element I'm looking for? If it does, I set my Boolean flag found to be true. And when I'm finally done, if found equals true, then the element was found. If not, then the element wasn't found. Okay, I've written my lambda expression. I'm going to call the for each function. I give it the vector. I give it my search function. And I verify that my search function meets the criteria. So it has to take an int and return void. It looks like it does. It has no return statement, so the compiler will deduce that it has return type void. And then I guess I'll just try compiling it. Now I'm going to get an error here. And the error is because I have not properly captured some things. All right, so it's complaining. It says, sorry, search element is not captured. So search element was defined outside of the lambda. It was defined as part of the enclosing scope, the search function. And then also found is not captured because found belongs to the outside scope. So I have to capture these. And I'm going to deliberately capture them individually. So I want to capture the variable search element as a copy. I never need to modify it, so I'm going to capture it by value. Remember that if you capture something by value, what you get is a read-only copy. You cannot modify it, but you can use it. I was given a search element when the function was called, when the search function was called. It never gets changed, so I'll just pass a copy of it in as a read-only thing that the Lambda can use. On the other hand, I have to modify my variable found. I want to borrow the variable found from the outside scope, and I will want to modify it in some cases. So I have to capture it by reference. Okay, so I capture search element by value. I think this is a good way of doing it. I don't need to modify it, so I shouldn't try and capture it by reference. Although I can, I shouldn't. So I'll try running that. And sure enough, there it is. Our vector in main does contain 6, it does contain 10, and it does not contain 187. And I was able to achieve that with no loops, although it was a little bit contrived. I was able to achieve that with no loops using a lambda expression. Now, there are lots of reasons that you actually would want to use a lambda expression instead of loops. And we're going to see that coming up when we return to that problem of pairing up elements of lists, where maybe it's not as simple as replacing one for each loop. Maybe we're replacing some hideous construction of iterators and things that we do not want to have to write ourselves. That's one reason why having this facility is so helpful. And finally, one more note about capturing. So I captured search element by value because I'm not modifying it. I think that's a healthy thing to do. I think it's good for anybody reading this to be able to see I do not intend to modify it. But just to demonstrate, I am allowed to capture it by reference even if I am not going to modify it because the compiler doesn't care. In fact, if you want to, you can even capture everything in the outside scope by reference with this notation. If I just put an ampersand by itself, that says bring in everything from the outside scope by reference. So you can now borrow and modify everything that would be available at this point in the function search by reference. So you can make modifications to it. This is valid, and I'm fine with this on an exam because I get that an exam isn't a very realistic scenario. I think it's not a good practice in general, because I think it's very important that somebody reading your code know exactly what the parameters of the lambda function are. And because the square brackets are a parameter passing mechanism, we should be specific. We should make it clear, what does the lambda expression really need? There could be lots of stuff in the outside scope. I don't want somebody modifying that code to think that the lambda expression needs all of it. I think it's great to be more specific and descriptive and write exactly what variables you need and how you need them. Do you just want to copy, or do you want to modify them? So although you can carry in everything by reference, I would really encourage you to build the habit of bringing in things you only need by value, and things you need to modify by reference, and don't bring in anything else.